Welcome to the channel. Today we will know about the nucleophiles and electrophiles. We will learn about these things, but by using some previous knowledge about the molecular orbital diagram. Suppose you have a compound, I hope you know about this, BH3, BH3, and NH3, this is ammonia. BH3 have a hybridization of sp2, but ammonia is sp3 hybridized. BH3 look like this, like three bonds in a plane having 120-degree bond angle, but it also have one empty p orbital. It also have one empty p orbital like this. This is the p orbital, empty p orbital, empty p orbital. But in ammonia, it have a lone pair, which is in sp3 orbital. This lone pair is in sp3 orbital. You very well know that the BH3 sp3 orbital. Okay, you very well know that BH3 is a hypovalent species because its octet is not complete and it have empty p orbitals, so it needs the electrons. The ammonia shares two electrons by forming a coordinate bond. This is coordinate bond, and with the help of this, boron completes its octet, and there is a sigma bond formation between them. What it do, it basically decreases the energy of this lone pair, and hence the whole thing get the stability. So basically we need to work on this bond, how this bond is formed. So generally here the BH3 needs electrons and it gets the electrons. So the species which accept electrons, basically one pair of electron, called as electrophiles, which we can resemble it via E plus, and the species which basically donates the electrons called as nucleophiles. Species which donates electrons called as nucleophiles. I can denote it by Nu negative. So how the molecular orbital approach works here in case of when there is the bond formation between nitrogen and boron. So what happen, the nitrogen have a lone pair in sp3 orbital and the p orbital is empty. So we can just say that the nitrogen sp3 have a lower energy as compared to the p orbital, empty p orbital of boron. Why we can say? The first thing is that the nitrogen lone pair have some s character which basically decreases the energy level, and it is also the electronegative. The other aspect is that it have lone pairs, right? It has some electrons, so electrons come to the lower orbitals according to the above principle. So let's suppose we have boron. Here boron have empty p orbital, empty p orbital, but a lower energy orbital, nitrogen sp3 have lone pair. Let's suppose when they will form bond, there can be two possibilities: constructive interference and destructive interference. So One possibility will make a bond which is sigma bond and which lowers the energy of the system, and this is sigma boron nitrogen bond. Fine. But it also a possibility that destructive interference will occur, and the energy of bond will increase, system will increase, and it will be the sigma star, the anti-bonding boron nitrogen bond. By applying the above principle, the two lone pairs will go to these sigma boron nitrogen bond, and hence we can see there is the bond formation between them, and that is sigma bond. So now we need to see how this energy levels of electrophile and nucleophile will work. Let's suppose we have two examples. I just recognize this boron as a electrophile or anything as a electrophile by just E having some kind of empty orbital. Let's suppose this is the empty orbital, and the nucleophile having energy just lower to the electrophile and having a lone pair or non-bonding electron. So, but the energy difference between them is really less. When they will form bond, they can have sigma bonded orbital and sigma star. So let's suppose if we have sigma bonded orbital like this is sigma, and we can also have sigma star. This is the sigma star. But one approach we can also see is that, let's suppose we have electrophile, empty orbital, and a nucleophile, but the nucleophile energy is very less, very less. Let's suppose this is the nucleophile energy. It have two pairs, two electrons, one pair of electron or non-bonding electron. So when we just make the molecular orbital, it will look like this. The energy of nucleophile does not decrease much. This is the sigma bond and this is sigma star. In such case, there is no much release in the energy. The energy release is very less energy release. But in such cases, when the electrophile and nucleophile have almost same kind of energy, then the sigma bond forms. It will decreases the energy very much. It decreases the energy of system. So more energy decrease. Or we can say, in such cases, when the nucleophile and electrophile have same kind of energy, then there is release more energy. They release more energy. It benefits much to a bond. So we can just say that the reaction can occur. Most of the reaction can occur when the nucleophile and electrophile have appreciable kind of same energy, and they will form a good bond by more release in the energy. So we just need a nucleophile having higher energy and electrophile with empty orbital having lower energy. So the energy difference between them would be less. And so the electrophile, we need electrophile with a LUMO, empty LUMO. What is LUMO? Lowest unoccupied molecular orbital. And nucleophile with HOMO. This is called as highest occupied molecular orbital. Highest occupied molecular orbital. molecular orbital MO. So this will form a good bond. So for a nucleophile and for a electrophile, this thing is important. Like we need a electrophile having LUMO, lowest unoccupied molecular orbital, and the nucleophile with HOMO, highest occupied molecular orbital. So if we just talk about first about the nucleophile, what nucleophile can be possible? We will discuss some of them. The nucleophile can be of charged, like negatively charged, or can be neutral. So there can be two cases. There can be two cases. Negatively charged or neutral. If I just give you some example of neutral nucleophile first, it can be like you have seen ammonia have lone pair non-bonding of electron in sp3. Again, water have two to lone pairs. Alcohols, ROH alcohols. Ethers. So these are neutral nucleophiles. Even the carbon double bond like alkenes. Here the homo would be pi bonded electrons. Pi bonded electrons. In the negatively charged species, we can have NH2 negative. It will also have non-bonding electrons. OH negative, like Br negative, Cn negative, halogens. We can also have BH4 negative. But in the BH4 negative, it is tetrahedral species. Negative charge is on boron. But the nucleophile here is sigma boron hydrogen bond, not this negative charge. Let's suppose if boron negative charge having four hydrogens BH4, just give their negative charge to a electrophile, then it will form five bonds. Is it really possible for the boron? No, it is not possible. So you can learn it by this. Hence here this boron hydrogen sigma boron hydrogen bond is homo. BH4 negative donates this thing. So these are some of the nucleophiles. If I just come to the electrophiles, again, electrophiles should have LUMO, which can be of again positively charged, or neutral. Like the best one we have positive charge electrophile is H plus. Why? Because it have empty 1s and it will be having of low energy, right? So that's why most of the reactions in which H plus participate as electrophile as one of the fast reactions, because it is just an acid base reaction. So the electrophile in which H plus act as electrophile called as acid. Fine. So H plus is one of the charged species and a positively charged electrophile. After this we can have carbocation like CS3 plus or Cr3 plus. The R can be any alkyl group and or just side atom. Carbocations, these are positively charged electrophiles. Or the neutral electrophiles, we can have like ALS3, ALH3, right? Like BS3, ALCL3. These have p orbitals as LUMO, p orbital, LUMO. Even in the CS3 plus, it also have p orbital as LUMO. Apart from this, the other neutral nucleophile, what can be possible? Like Br2, Br2. Why? Because this bromine bromine bond, that sigma bond is really weak. Yes, it is weak. Why it is weak? Because bromine and bromine have a like more radii, so this would be a weak bond. Even if you just make the diagram of molecular orbital, you will see the sigma and sigma star of very low energy. Like this is sigma and this is sigma star, sigma star. So it is very easy that the bromine will break because the energy is not very high of the sigma star. This is Br2. And even here the LUMO is sigma star in Br2 fine. The next which can be possible is C double bond O. Let's suppose here R and R group is attached, R and R dash. It can be different or same. Here the electrophilic center is this, like carbon. It have pi star as LUMO, pi star as LUMO, pi star as LUMO, pi star.